Welcome to this explainer, where we're taking a structured look at the incredible analytical science that protects our daily lives. Every single day, we interact with thousands of chemical compounds, and whether we realize it or not, our health and safety absolutely depend on knowing exactly what those compounds are. So today, we are demystifying the ultimate truth teller of the scientific world, the GCMS system.
Think about your morning routine for a second. You probably grab a glass of tap water, maybe eat some fresh fruit, or take a daily health supplement. We buy these things trusting the label completely. But how do we actually verify what's inside the bottle? How do we really know the water is clean, the fruit is pesticide-free, or that the supplement isn't laced with something dangerous?
Take a standard bottle of omega-3 fish oil, for example. The label claims it's pure, high quality, free of additives. But analytical science is the real mechanism of trust here. It's what separates a marketing claim from the hidden reality. By using instruments like the GCMS, laboratories can look right past that label to verify if you are actually getting pure omega-3, or if you're secretly ingesting heavy metals, dangerous toxins, or banned substances.
So, here is our game plan for today. We're going to follow a single sample through 6 steps. 1. The mechanism of trust. 2. Prepping the liquid sample. 3. The GC separation racetrack. 4. MS shattering into fingerprints. 5. Calculating the exact amount. And 6. Validating the absolute limits. Let's jump right in.
Section 1. The mechanism of trust. Verifying the invisible. Step 1 is simply understanding that before we can identify a hidden toxin, we have to respect the intense sensitivity of our machinery. You cannot just pour river water or a crushed-up vitamin straight into a multi-million-dollar instrument. That brings us to Section 2, prepping the liquid sample, isolating the target. See, environmental and biological samples are incredibly complex. They're just packed with proteins, salts, and background junk. So our very first task is isolating our specific microscopic targets from the rest of that mess.
The prep pipeline follows a super strict sequence. Once we collect our liquid, we quickly pass it through an incredibly fine 0.45 micrometer membrane filter, mostly just to get the physical particulates out. Next, we preserve it, often by dropping the pH to below 2 to stop any bacterial breakdown. And only then do we extract the target compounds. It's really fascinating how this extraction works in practice. Laboratories might use solvents for a liquid-liquid extraction, or they'll pass the sample through solid-phase extraction cartridges to trap the specific chemicals they want. From there, they dry the extract and use a gentle stream of high-purity nitrogen gas to evaporate whatever solvent is left. So, what we end up with is a highly concentrated, perfectly pure final GC vial containing only our target molecules. Moving right along to Section 3, the GC separation racetrack, sorting molecules by speed. Now we get to the instrument itself, starting with the first half of our machine, the gas chromatograph, or the GC for short. This is where we sort the molecules by their physical properties.
Looking at the system's overall architecture, it all kicks off with the autosampler. It acts with total robotic precision, injecting exactly 1 microliter, literally just a microscopic fraction of a drop, of our prepped liquid into a highly heated injector. At 250 degrees Celsius, that liquid is instantly vaporized, right into a gas. Once it's a gas, a carrier gas, usually helium, pushes this chemical vapor into an analytical racetrack. We're talking about a 30-meter-long, incredibly thin glass column coiled up inside a specially designed oven. And just like a real foot race, not all molecules run at the same speed. The highly volatile compounds are fast runners, don't interact much with the column, so they sprint to the finish line quickly. Meanwhile, the less volatile compounds, the slow runners, lag behind and exit later. The oven actually gradually heats up to force those slow runners out.
And as each unique group of molecules finally crosses that finish line, the detector registers them, generating a pulse on a graph called a chromatogram. Every single peak you get on a chromatogram corresponds to a different compound exiting the column at a very specific retention time. That's our proof that the complex mixture was successfully separated over time. Which leads us to Section 4, MS shattering into fingerprints, identifying the unknown. The crucial thing to remember here is that while the GC beautifully separates the mixture into these neat individual peaks, it actually doesn't tell us what those molecules are. A peak is just a pulse of data. To figure out the true identity, we need the second half of the machine, the mass spectrometer. As each separated compound leaves the GC racetrack, it flies directly into the mass spectrometer's ion source. And here, something violent and honestly kind of amazing happens. The neutral molecules are bombarded with high-energy 70 electron-volt electrons. This extreme energy knocks an electron clean off the molecule, making it highly unstable. And because it's unstable, the molecule completely shatters into smaller, charged fragments.
But here's the magic. It doesn't shatter randomly. The laws of chemistry dictate that a specific molecule is going to predictably shatter in the exact same way every single time. This creates a mass spectrum, which is a mathematically unique fragmentation pattern. It's quite literally a molecular fingerprint. The system takes this fingerprint and runs it against massive global databases, like the NIST library, to find a perfect match and absolutely confirm the chemical's identity.
So, to summarize the beautiful dichotomy of this whole instrument, the GC gives us the where, based on time, it separates the mixture and gives us a retention time via the chromatogram. But the MS gives us the what, based on molecular identity. It takes that separated peak and gives us the fragmentation pattern to tell us exactly what chemical we're looking at. By synchronizing these two distinct data streams simultaneously, the software mathematically verifies the absolute truth. You look at a specific peak on the GC timeline, and then you look at the MS fragmentation pattern underneath that exact peak. Together, they confirm without a shadow of a doubt exactly what chemical is present in your sample.
All right, Section 5, calculating the exact amount, translating signal to concentration. Identifying a dangerous substance like a pesticide in your water is really just half the job. The next immediate question is always, how much of it is there? Is it a harmless trace or a toxic dose? We have to quantify it.
Before we can measure our unknown sample, we essentially have to build a ruler. We do this by taking a known, certified, stock standard of the chemical and performing a highly precise half-concentration cascade. So we take a 160 parts per billion solution, dilute it exactly in half to 80, then 40, then 20, and 10. We also run a pure blank with absolutely nothing in it. We run all of these known amounts through the machine first to see exactly how big of a signal the machine gives for each specific concentration.
Once we have those reference points plotted from our known standards, we run our completely unknown sample. The machine's going to spit out a peak area. But how do we evaluate that unknown peak? Like, how do we turn an electrical signal into an undeniable real-world concentration?
Well, we use a calibration curve. I know, flashbacks to high school algebra. But y equals mx plus b is about to become your best friend. We plot the responses of our known standards to draw a perfectly straight line. When our unknown sample runs, let's say it gives us a peak area of 153,000. We just plug 153,000 into the y variable of our linear equation and solve for x. Just like that, the math tells us that our unknown sample has an exact concentration of 15.2 parts per billion.
Finally, Section 6, validating the absolute limits, ensuring legal and scientific trust. Because that number we just found, 15.2 parts per billion, is incredibly powerful. But for these results to actually function as a mechanism of trust, especially if they're going to be used in a courtroom to sue a polluter or by regulators to pull a dangerous product off the shelves, they absolutely must pass strict mathematical validation.
Laboratories have to maintain a rigorous quality assurance dashboard. They can't just run the machine and trust it blindly. They have to prove that their linearity hit an R-squared value of 0.99 or higher, meaning their calibration curve is nearly perfectly straight. They must run identically spiked samples repeatedly to ensure their accuracy recovery falls strictly between 70% and 120%. Basically, every single step must be completely mathematically defensible.
And to wrap it up, we define our absolute limits using signal-to-noise ratios. If the chemical signal is just barely taller than the background static of the machine, specifically a multiplier of 3.3, that establishes our limit of detection, or LOD. We know the chemical is there, but it's too faint to measure accurately. However, if the signal achieves a stricter multiplier of 10 times the background noise, that defines our limit of quantification, the LOQ. This is the absolute lowest amount we can accurately and legally put a definitive number on.
It is just wild how this highly structured, complex journey transforms a single microscopic drop of liquid into an undeniable truth. From precise prep pipelines and 30-meter glass racetracks to molecular shattering and linear equations, the GCMS is the ultimate guardian against the unseen. And it kind of leaves you wondering, as you go about your day, eating, drinking, and using countless products, what other hidden realities